All right, so we had a few questions from the 2016 free response for the AB section, specifically 1D. So let's go over that real fast. So let's go over to my share screen. Share that. Okay, so and the question, okay, this is the question, so we're on the same page here, is we have, after you use that table, of course, the very last question, actually, I think it's kind of hard. It says, notice you have this function R, which is up here, and then you have this function W, which is given to you here. All right, they tell you this is differentiable, which means it's also continuous. Okay, and they tell you also kind of important, tell you R of t is differentiable and decreasing, so it's decreasing the whole time. And this function right here, even if you didn't know that, this is also a decreasing function because this is a negative exponential, meaning the exponent is negative, so it's going to be decreasing from left to right. Okay, so all of that is going to kind of play part into what we're going to talk about. So the very last question, it's actually kind of a tough question. It says, for zero, between 0 and 8, there is a t where the rate at which the water is pumped into the tank is the same as the rate at which the water is removed. And let me see, the water is pumped into the tank. So this is the pumping into the tank, and function R is how fast it's being removed. All right, so in essence, how to do this, if we had the function for R, it would be very easy. All we have to do is basically set R and W equal to one another. All right, the problem here is that we don't actually have a function for R. We actually have a table, which kind of makes it more difficult. Okay, so how we would do that? Okay, so again, this is how I did it, right? So keep in mind that I'm going to write a couple of numbers here first, and you may or may not understand why I'm doing that, but just hang in there, right? So this is 1D. So before I turn into the screen, I'm going to write, start over on that one. Let's see, I want to know, and again, I'll explain why I'm looking for this, but I'm basically going to look for W of 0, meaning I'm going to plug in a 0 into the function W. And I also want to know R of 0. Okay, now R of 0 is given to me in this table. So R of 0, I know that when t is 0, R is going to be 1340. All right, so, and then I'm also going to find out what W of 8 is. So I have to plug an 8 into the function 2000 e to the negative t squared over 20. All right, and I also want to know what R of 8 is. Now, R of 8 is on the table. All right, and again, you may not know why I'm doing this, but I'll show you here in a second. So R of 8 is 700. Okay, so let me now switch to my screen. And if at any moment you don't see what I'm talking about, Emerson, just kind of stop me and be like, I don't know what you're talking about, and I'll stop. Okay, so now, if you plug this into your calculator, okay, W of 0 is 2000 and W of 8 is 81.524 or something like that. So here's what I'm getting at, right? Say that you didn't know that. It's asking you where the rate is the same. Now, on the key that I sent you, I drew a picture, but remember, a picture is not acceptable as an explanation for the AP exam, okay? So I said that between 0 and 8, let's call this x-axis, let's call this time, and up here is either going to be the rate. This is going to be some kind of rate, right? So we're gonna say that 1340 is here, of course, not to scale, and I know it's decreasing. Don't know if it's decreasing exactly like this, but let's say that it is, okay? And then we also have function W, and then function W starts off a little higher, right? So W starts off a little higher, like at 2000. But by the time it goes to W8, it's actually, and let me put that point over here, 700, I think was the number here. So let's say that that point right here, where this is set, the height is 700. So this function right here actually, at some point, drops below this other function. So I know there's a point precisely right here, right, according to the picture, where the two functions are going to have the exact same rate. Okay, so this y-axis is the rate. So how will we do that? And this is the tricky part, right? So, and honestly, I didn't see that coming. So I knew from the beginning that what I was looking for is I was trying to find out when W of t is equal to R of t. I knew that that's what I needed to do, but unfortunately, I do not have an actual function for R of t. I just have a table, and the table is not enough. Okay, so what I kind of looked, honestly, I looked at the key to figure out how they did it, but what they did, which is pretty clever, I guess, is basically, let's do this, right? If I subtract r of t, that's going to give me 0, okay? So basically, I'm trying to figure out where it crosses the x-axis, if you will, okay? So what we're going to say is that if we have w of 0 minus r of 0, okay, so remember, w of 0 is 2,000, so it's 2,000 minus 1,340. What is that, like 660, I think? But the point is that it's a positive value. Okay, so that's why they write it like that on the key. It's a positive value. Now, and at the end, all right, if I have w of 8, if I subtract those two values minus r of 8, right, notice that w of 8 is 81, and this is 700. So 81.524 minus 700, that's going to be a negative value. Okay. Now, all of those are facts. Okay. Now, what we're going to actually invoke here, if you want to call it that, like it's witchcraft or something, is we're going to use the mean value theorem to explain that that's true. Now, if I want to know where something's 0, all I have to say is that at some point you're above the x-axis, if you will, and at another point you're below the x-axis. Does that make sense? So you have to write this, since w of t minus r of t is continuous. So basically we're considering this one function, right? It's continuous. Let's see if I can spell continuous. I think I did it right. Then you can say the intermediate value theorem, which I will abbreviate. I can't even say that word. The intermediate value theorem guarantees, and then basically you're at that point you're just kind of writing down what the intermediate value theorem states, which guarantees at least one time between 0 and 8, such that, and I usually write an ST, I mean such that w of t minus r of t is equal to 0, which basically implies that w of t is equal to r of t. So again, just to kind of go over everything I just said, okay? First of all, we know that's true. You don't really need that picture to understand this. But what I said on here, I'm just telling you that that's a really fast way to be able to know that it does happen, okay? Now, what we're saying here is that we're going to set that equal to each other. Now, once we subtract this function here, this becomes just pretend it's a parabola or whatever, just some function, right? Now, if I want to know if a function actually went through the x-axis, right, which we're going to call this 0, this would be going through the x-axis, then what I would say is if I have a y value that's above the x-axis, which is what I'm saying here, I have a y value that's greater than 0, which is positive, right? And I have another y value that's below the x-axis, okay, that's what that means. If the function is less than 0, right, negative, if this function at 8 is less. So if I have a point over here and a point down here, I have a positive and a negative that I must have gone through the x-axis, which is 0. All right, now very important, you always have to say that this is continuous. All right, you always have to state that this is continuous, and actually a lot of the times I write n differential, kind of important. So I normally write because this function, remember this is one single function now, is continuous, you have to state that, then the intermediate value theorem basically guarantees what I just said. I mean, doesn't it make sense if I have a positive value and a negative value? Well, between those two values, if it's continuous, it must go through 0. Does that make sense? Emerson, go ahead and unmute yourself and let me know if that makes sense or not.
Yeah, that makes sense.
Okay, so, by the way, my phone has been typing everything I've been saying, which is like 3 pages. I don't know why it's doing that. Okay, so now let's go over to the second part that you asked me. So any questions in 1D beyond that? I think question number 1 for the most part is pretty straightforward, except for that.
Yeah.
Okay, so let's go over to number 2. You said 2C. Okay, so let's take a look at 2C. Okay, so 2C is one of those classic questions that I can almost guarantee that you will have on there. I'm pretty sure. Let's see. So we're talking about this part right here. I find the position of the particle at time t is equal to 0, right? So now on this question right here, I can almost guarantee, I mean, almost, keyword almost guarantee that you're going to have something like this in your AP exam, because this kind of tests you on whether you understand or not what the actual fundamental thermic calculus is. I know what it is. I may not be able to pronounce it, but I know what it is. All right. So here's the deal. Let's, okay. So I'm going to write some information here. Okay. Very important. All right. So this is the question you should get right every time, because first, it's not too bad once you understand it, but second, I promise you will be there. All right. So they tell us at the beginning of the problem, this is problem number 2, that we have this velocity function. And this one's not like, okay, 1D, the one I just showed you, that's kind of a tough one, okay? I highly doubt you're gonna see something like that on the AP exam. I guess you could, but that's kind of a tricky one. This one, on the other hand, is a lot simpler to do, so therefore you might be able to see it, right? So they give you the velocity. Now, I'm gonna write this in a strange way. You can use another variable if you like, but they tell you on this problem, the position of the particle at t is equal to 4 is at 2. All right, it says x is equal to 2. So I'm going to write that in a strange way. All right, this says that at t is equal to 4, the position function is at 2. All right, does that make sense? And you do need to unmute yourself and tell me yes or no.
Yeah, I think so.
And again, if you want to write it like this, I don't care. Does that make sense? Use whatever variable you're comfortable with. People don't like to use this because it throws them off, because they keep thinking this is the x value. Well, in this case, this is the x value and this is the y value, but it's only because it's moving in a horizontal position. Does that make sense? So do you want me to use this one or this one? I want to use the one that you're less confused about.
It doesn't matter. I get both of them.
Oh, good. That's what I'm talking about. All right, so now let me see what the question's asking one more time. I'm pretty sure I know what it's asking, but a lot of the times, like somebody said to me, sometimes I just don't understand what is it that I'm looking for, right? Can you see this okay? All right, so we're finding the position of the particle. So we want to know the position of the particle at t is equal to 0. All right, so back to my screen. So what I'm looking for, according to what I wrote, is I want to know what this is equal to. I don't know what that's equal to. All right, so first, I am given the velocity function. And remember, at this point, I have a calculator, right? So I'm going to integrate this. When I integrate the velocity function, I get position. Remember, position, if you take the derivative of position, you get velocity. The derivative of velocity is acceleration. So if you go backwards, the antiderivative of velocity is position. So anyway, so we're going to integrate the velocity function. And now this is the trick that I'm talking about, if you want to call it a trick. I'm going to write this because I know when I integrate this, I get the final position minus the initial position. Okay. Now, in this case, I don't really want to know, this is basically the displacement right here. It doesn't say to find the displacement. What it's asking for is find the exact position at x is equal to 0. So what you do is I'm going to add this right here. I'm going to add this to the left side. So I'm going to say, well, actually, I'm going to subtract this guy because that would be easier. Now, let me see how do I want to do it. Basically, it's almost like just consider this some kind of function and just subtract or add it, but I'm going to add this to this side. I will do that. And then I'm going to subtract all of this to the right side. So I would end up with x of 4 minus from 0 to 4, the integral of velocity from 0 to 4 dt. All right, that's the key. Do you understand that, Emerson?
Yeah.
Okay, so and then at that point, don't kill yourself. I'm not going to try to do this by hand, all right, especially in number 2. So I'm going to go to my calculator. Remember, at this point, I'm just showing you what I would do. I'm going to type this in. Make sure you're typing it in correctly. Make sure that you are in radians. Right, if you're not in radians, then it's going to give you the wrong answer in this one. Okay, I don't care to graph it. I'm gonna go on and I'm just gonna press, let's see, remember x of 4, right? X of 4 was equal to 2. So this is 2 minus this integral again. So what I'm trying to tell you is please don't do this integral by hand. There's no point. Okay, so we have 2 minus math number 9, integral between 0 and 4. And in this case, I'm going to write y1. So it's alpha, trace, enter, dx. And that's the answer. All right, any questions on that?
No, that makes sense.
All right, so make sure you really understand this one, right? You, on these type of problems, every single free response problems that I did, 18, 17, 16, they had at least one question, sometimes two. They had this sort of problem, okay? All right, so let's move on now. So 3C, you said you don't know, and it could be a mistake on that part, I don't know. You said I don't know where the y values came from in the table. Okay. Oh, okay. Yeah, that's fair. So let's look at number 3. Let me, so number 3C. Okay. Okay, so you have this is the graph of f, and they tell you that g basically is the integral of function f. So you can actually call this g prime, and that was sort of the key on this one. Now, the problem that keeps coming up a lot is absolute minimum, but absolute minimum, and then or sometimes absolute maximum. All right, so that comes up a lot. All right, so this is kind of an important question. So you said you don't know where the numbers in the table came from. All right, fair enough. So to figure out, here's the deal. To figure out absolute max or absolute min, you're gonna have to do a couple of things, okay? You're gonna have to figure out, so at this point, I'm gonna go to my screen and I'll show you how I'm getting those numbers here in just a second. First of all, I have to find what's called my critical values. And that's normally where the derivative is 0. Let's call it g prime of x is 0. I want to know where that happens, okay? And so I'm going to use that. Now, technically, you are supposed to check every one of those, okay? And in this case, it does help to check every one of those. I didn't do that originally because I knew that it had to go through it for it to be a maximum or a minimum. Does that make sense? So technically, you have to check, all right, if I were doing this and I hadn't seen quite part D is the reason I'm about to do all of them, is that if I have a graph that literally crosses through, like say it's doing something like that, this point right here, I would definitely check. But if I had something like this, I wouldn't check this one because this is still decreasing. So it went from decreasing, remember, assuming this is the derivative here, it went from decreasing 0 to decreasing. So that's not going to be a max or min. It can be, all right? But anyway, so this is how I figure out those points, okay? Because you're going to need them on part D anyway. So I need to figure out where the derivative is equal to 0. And now if we look at our table, that's basically every single x value where you're touching the x-axis at least. So there's one critical value here, -2. There's another one at 2. There's another one at 6. And there's another one at 10. Okay, so you have 1, 2, 3, 4. You have 4 critical values. Are you with me? Now, when I did part C, I only checked this one and this one because, in terms of critical values, I only checked those 2 because that's actually the points where you went from from negative to positive, which means you went from decreasing to increasing, which means you definitely have a relative minimum, but you could have an absolute minimum there too. And then right here, you went from positive to negative, which means you went from increasing to decreasing. So that's definitely a relative max, but it also could be an absolute max. Okay, so I know I said a lot, but here's the deal. Here's where they came from, all right? So what I have to do, first of all, is I have to figure out the endpoints, all right? So you always have to do that. Check the endpoints in order for you to do the in order for you to find the absolute maximum, you have to check the endpoints. All right, so basically in this table, I'm going to write x, and here's the key to this. All right, so these are the endpoints. And I'm actually going to write all of them because I may need them later. All right, so I'm even going to write, the ones that I know are not going to be absolute max or mins because they don't go through the x-axis. Okay, which is 2 and 10, I think. Oh, I wrote it here. 2 and 10. No, it's yeah, it's 2 and 10. Anyway, so I have to figure this out in regards to f of x, or in this case, g of x. Okay, so let me erase that. So I have to figure out for g of x. Now, they tell me in the problem that g of x is equal to the integral between 2 and x of f of t dt. So where I'm getting this from, first of all, I got this just for this are all critical values, right? Remember, this are the endpoints. These two are my endpoints, and everything in the middle is where the derivative was equal to 0. So that's where I got that from. Okay, now, as far as the y values, I'm just using this a lot. So the first one, for example, which I did earlier, I'm pretty sure. Maybe I didn't. The first one, all right, g of -4, for example, would be the same thing as 2 to -4 of f of t dt. Okay, and f of t dt, and I have to then, because that's smaller, I have to switch that. So I have between -4 and 2 f of t dt. So my goal here is to figure out the area under the curve on that graph between -4 and 2. Now, between -4 and +2, I mean, I kind of have a picture here. And you can almost, they did it so simply that you don't have to spend a whole lot of time trying to figure out triangles. But this is one triangle that's a negative, right? Sorry, my dog is drinking water very loudly. Now, this triangle is of the same length. So this negative area and that positive area cancel out. And I only have to attribute for this little area right here, which is 2, is 1/2 base times height. So it's 1/2 4 times 2, which is going to be 4, I believe. Or -4, yeah. It's going to be +4, but because I have this negative on the outside, it's going to make that a -4. Does that make sense, Emerson?
Yes.
Okay. So that's basically what I was doing. So for the next one, all right, so I'm going to do a couple, and I'm going to go ahead and assume you can do the rest after that. Between 2 and -2. All right, so I have to do the same thing. I have to switch those two. I have to make this, and you understand why I'm switching that, right? I have a negative here. I have to have the smaller one on the bottom.
Yeah.
So basically, I'm looking for the area under the curve between -2 and +2. So between -2 and +2, that would be this whole triangle right here. So it's base of 4, height of 4. So it's 1/2 4 times 4, right? So it should be -8. So you can even write it like this. I mean, you can write it all out. I'm just not doing that, but this is -8. And this is where this comes from. Does that make sense? And then g of 2, well, g of 2 is equal to, well, that one's an easy one. We can definitely do that one. G of 2 would be the area under the curve between 2 and 2. Well, the area between 2 and 2 is nothing. That's just a line. Okay, so I can put a 0 here. Does that make sense? And then so on and so forth. So for example, in 6, I did the same things. I'm just figuring out the area between 2 and 6. So I'm looking at my triangle between 2 and 6. So between 2 and 6, that's another triangle of height 4, excuse me, base 4, height 4. So it looks like it's also going to be a 8 in this case. Now remember, this one was -8 because I had to switch those, right? So, and again, if you keep doing that, then you get 0 for this one, and then you get -4. So to answer your question at the end, it's asking for the absolute max and absolute min. So this is actually your justification. So you don't have to say like, well, because this one's higher, that you don't have to say anything. That table for them, like, with this, is your justification. So at that point, you just have to tell them, hey, the absolute max is at, well, since I want the value, they actually want you to write what the number is. And absolute min is at g of -2, which is -8. Does that make sense? All right. So you understand where the y values came from now?
Yeah, I just didn't think about the area under the curve thing.
Yeah,
So,
that's
yeah.
very, very important. All right, so let's go on to number 4. You said 4, I don't understand the 1/3. Okay. Yeah, on this one I can just show it to you because I think that is just a minor thing. Assuming you can follow all of this, right? So hopefully you can follow, right? We're looking for the particular solution. So when it's asking for that, that means I have to do, what is that called? Oh, I know how to do it. I just keep forgetting. What is that called? Separation of variables. Excuse me. So you're going to take that, do separation of variables. So this is what I'm doing here, right? I divided both sides by y² in this. Now this part right here, you can do u substitution. Hopefully at some point, maybe not this year, but if you have to take this type of particular class again, then this, as soon as I see it now, I know it's a natural log. What's the derivative of x? It's just 1. So see what I'm saying? This is just going to be the natural log of x minus 1. Now this one right here, hopefully you can follow, and it looks like you were following all the way to here, and you understand where the 1/3 came from, right?
Yeah.
Yeah, natural log of 1 is 0, so it's -1/3. So you're asking me why switch signs right here or right here? Or at the very end.
At the very end, I think.
Okay, so here's the deal, all right? Remember, I am trying to find a particular solution, meaning I want to get y is equal to. All right, that's what I'm looking for. So if you actually look at the key, they did actually less work than I did because they didn't even find a common denominator here. They just said, screw, we're not going to do that, which is fine. But anywho, it's still, so when you look at the actual key that I sent you from me and from the actual AP board, they look different, but they're the same, right? So in this one, I found a common denominator. So I multiplied top and bottom by 3 here. So I was able to write this as one fraction. Now, hopefully you're able to see now, because this happened a couple of times, that when you have like 1/y, assuming you have a fraction on the other side, you can just flip that. All right, so that's what I did here. I just flipped it. Now, because I'm trying to get rid of this negative, I'm just going to multiply both sides times a -1 or divide by a -1. It doesn't matter. But when I make, remember, when I make this part negative, I'm only going to make either the numerator negative or the denominator negative, but not both. All right, so that's why I put a -3 only on the top.
Okay.
And let me see, I understand why the 1/3 and the natural log of x1 switch signs. Okay, does that answer your question? I'm not really sure that it does.
I mean, kind of. It's just because it's different than the answer key that I looked at.
So here's the deal, right? What they did in the key, and if you want to know what they did in the key, let me see. Which I'm just trying to show that it is truly the same. So they started off, they were still here. Okay, so they were still there. And let me see what they did. But I'm pretty sure all they did was,
Oh, is it because you divided by the negative?
Yeah, so right here they divided by the negative or whatever, so they made this positive and then decided to write that first here.
Okay, yeah.
You know what I'm saying? And they made this negative and decided to write it second, but they did switch the signs. And as you can see, they didn't care about having this as one fraction. They just went ahead and flipped it over. They just put this all over 1.
Right. I guess I just missed that, but it's okay. I get it now.
Okay. That's a minor one. Let's see. Now you said 6C. Let's see, what is 6C? Oh, yeah, that was a little tricky one for sure. Let's look at 6C then. I think that's one of the ones that I officially missed. Makes you feel better. Or might make you feel worse, I don't know. Let's see. All right, we don't have to do this anymore. 3. So everything else in number 6 was fine then.
Yeah.
Okay, good. Another piece of paper here. All right. So they're asking me to evaluate this right here. Okay. So here's the weird part with this one, right? What I would have wished that, and that's sort of where I missed it, that would have just been f double prime of 2x, but it's not. Okay. Now, what's gonna make this different, okay, is pretend that this is some kind of function, and notice that you basically have a function, and inside that function you have another function. All right. So this is basically it's a chain rule, if you will, but it's backwards. So I know that I'm supposed to take basically the inside, and I'm going to have to take the derivative, which is going to be 2 dx. Are you with me? So I'm going to have to do basically that, and you're going to see how this hopefully makes sense after you do that. And if you divide that by 2, well, because I don't need that 2. Of course, I have the 2 here, but I don't have another 2 in this integral. So I'm going to divide both sides by 2. So essentially what I end up having is f double prime of u du with a 1/2 out here. Okay?
Yeah.
When I take the antiderivative of f double prime of u, that's just going to give me 1/2 f prime of u between, and I don't really like to write 1 and 3 because at that point I should really switch it because people are probably going to think that I should just plug it in. But really at that point, go ahead and switch it back to a 2x. You're going to go between 1 and 3. Are you with me?
Yeah.
And the reason I said I wish that would have just been x, because you could have just done f prime of 3 minus f prime of 1, but you can't do that in this one. So anyways, this is f prime, and then when you plug in the 3 here, that's going to make it a 6. When you plug in the 1 here, that's just going to make it a 2. And then you're going to have to go to the tables and figure out what those 2 numbers are. So f prime of 6, f prime of 6 would be 7. No, wait, 5. And f prime of 2 would be -2. That's 5 minus a -2, I believe.
Yeah.
I don't know where I put the key, but surely. Yeah. And I forgot about the 1/2. So yeah, 5 minus a -2, but with the 1/2 on the outside, it's going to make it 7/2.
Yeah.
Does that make sense?
Yeah, it does.
Okay, so let me stop the video here. Hang on.